Hello, welcome to our second video lecture. I'd like to start by kind of doing a quick review of the stuff that we covered in the last week of class before spring break, related to capacitors, inductors, and the solution of first-order differential equations. So let's just do a review of capacitors to start out with. So capacitors are governed by the fundamental relation you see on your screen, where the current is equal to the capacitance times the derivative of the voltage. Capacitance, represented usually with a C, is given in units of farad, which is usually abbreviated with an F. The power of a capacitor is calculated using the same P equals VI equation that we introduced you to in the beginning of the semester. If you substitute the fundamental relation for the capacitor into the power equation, then you can see that the power is equal to C times V times dV dt. The important thing when considering the power, however, is just as with Ohm's law, we have to make sure that we use consistent signs according to the sign convention. So just to remind you, what this means is that the power is written with a positive sign if the current is entering the positive terminal of the capacitor, and it's written with a negative sign if the current enters the negative terminal of the capacitor. The energy is defined as the integral of the power over time, and it can be shown that the energy for a capacitor is given as 1/2 C times V squared. The critical thing to understand about capacitors, however, is how they behave both instantaneously and over the long term. And the key to really understanding capacitors and how they behave is to understand really the fundamental meaning behind the fundamental relation, which is shown here on the slide, I equals C times dV dt. So all of the deductions that we're going to make actually relate to the derivative of the voltage itself. So let's first consider what happens when you have an instantaneous change. What do I mean by an instantaneous change? This would be the case, for example, where you had a capacitor that was without any charge and alone and by itself, and then you suddenly connected it, let's say, directly to a battery, right? So now you have a jump in what you're applying to the capacitor. In this case, it may be the voltage. So the question is, though, how do you represent those types of changes? Remember that the derivative is the mathematical way of expressing change. And having an instantaneous change amounts to having something like a step function where you have an infinite slope at a particular time, which corresponds to whatever the time of the event is. The key thing here, though, is that no physical capacitor can handle infinite voltage or current. So whatever variable you're taking the derivative of, you have to make sure that that is never infinity in the real world. So in the case of a capacitor where the current is dependent upon the derivative of the voltage, what this means is that in real life, the capacitor can't handle an infinite derivative of voltage. The consequence of this is that the derivative of voltage has to be finite. In other words, we have to have a continuous function of voltage. We cannot have a discontinuity, such as what I've drawn on the graph of the slide that you see here. So this now causes there to be a kind of constant continuity constraint. So let me just try to write on the board here what I'm referring to. Continuity. What I mean by continuity is that the voltage must be a continuous function of time. And a corollary of that requirement, then, is that supposing that a particular event happened at t0 minus represents the instant before the time t0, whereas t0 plus represents the instant immediately after the event at t0, we must require continuity, which means that the voltage immediately before the event should not change when we look at it immediately after the event. This will prevent any kind of sudden changes or mathematical discontinuities in the voltage function that would cause there to be an infinite derivative. And, essentially, if you did something like that in real life, it would cause your capacitor to blow up if you did something like that. So the capacitor wouldn't be able to pull voltage that way. So this is going to be something that we're going to take advantage of when we look at how capacitors behave when we're looking at initial conditions. Let's now consider, though, the next kind of important endpoint of behavior, which is how a capacitor behaves in the long term. So suppose you had some battery that you've now connected to this capacitor, and you're charging your capacitor. What happens after a long time? Well, just as with any mechanical, electrical, or other system, eventually all of the transient behaviors will die down, and eventually the system will come to rest. What I mean by the system coming to rest is that nothing will change anymore. It's kind of like if you take a ball and you roll it downhill, you can model kinematically what's happening to the ball, but eventually, due to friction, the ball will eventually slow down and then finally come to stop somewhere. And unless any further forces are applied, that ball will stay in the same position and it won't move at all. And so if we look at now what happens to the capacitor when there are no more changes, no more dynamics anymore, how can we look at what happens to the capacitor? Well, we can model that by considering the fact that in this case, the derivative will equal to 0. That's the mathematical way of stating essentially that there's no change. This is known as the steady state condition of the system. And if we look at what happens to the capacitor when we substitute the derivative of the voltage equal to 0, we can see then that the capacitor current must be equal to 0. So what this means is that when all of the transients have died down and the circuit is in steady state, the capacitor behaves like an open circuit. It will not pass any current through whatever branch it is on, but it can have a voltage across it. We can do the same kind of deductions on an inductor. So an inductor is also an energy storage device like the capacitor, but in this case, the voltage of the inductor depends on the derivative of the current. It's related through the parameter L, which is the inductance, and it usually has units of Henry, which is abbreviated with a capital H. As before, the same power relation P equals VI holds true for inductors, and if you substitute the fundamental relation, then you can find that the power equals the inductance times the current times the derivative of the current. And as before, we also always have to make sure that we're using signs in accordance to the sign convention, which means that we are using a positive sign of power when the current is entering the positive terminal of the voltage. If we use the fact that the energy is the integral of the power, it can be shown that the energy of an inductor is 1/2 L times the current squared. How does the inductor behave, both in short-term and long-term conditions? Well, now we have to look at the derivative for the inductor, but in this case, the derivative term is a function of the current, not the voltage. So we have to consider the fact that we don't want di dt to go to infinity. And so now in the case of the inductor, the continuity constraint is going to be the fact that just before an event happens at t0, whatever the current is, I of t0 minus, that should equal and remain the same instantaneously after the event. So this is going to be our continuity constraint, and it's going to ensure that the inductor current is a continuous function of time, and it will prevent any kind of abrupt discontinuities that would result in a situation that the inductor wouldn't be able to handle. So this is going to be the main relation that we use to help us deal with initial conditions. Secondly, we should consider what happens when the inductor is in steady state. So again, this is the case where a long time has passed, all the transients have died down, and we want to see what the situation is in the circuit. And so to understand, again, what the inductor will behave like, let's now substitute that the derivative is equal to 0. In this case, we're taking the derivative of the current and setting it equal to 0. And using the fundamental relation for the inductor, that means that the inductor voltage now must be equal to 0. V equals 0 corresponds to a short circuit. So what that means is that when all the transients have died down in steady state, the inductor essentially behaves like a short circuit. It won't permit there to be any voltage across the inductor, but it will just directly pass whatever branch current is going through it. So let's see how we can use this interpretation and knowledge of the fundamental relation to help us to better understand how circuits behave when we connect them, how capacitors behave when we connect them to resistive circuits. So let's look at the circuit that we have on the screen now. It consists of a capacitor, which has a value of 100 microfarads, and it's connected to a resistive network through a switch. But the switch has a little bit of an interesting motion. For T negative, it's connected to position 1, meaning that it's connected to the 3 kilo ohm resistor and the 24 volt supply. But at T equals 0, the switch changes positions to position 2, and now the capacitor is only being supplied by the 4.5 milliamp source on the right-hand side of the circuit. So how does this behavior of the switch affect the capacitor? What is the initial voltage of the capacitor? What is the final voltage of the capacitor? How would we determine what that is? Let's first consider, just now again philosophically, without really doing any calculations quite yet, what the timeline for the circuit would look like. So consider that we start like a long time before 0, like minus infinity or whatever. When we first kind of put the circuit together, let's assume that there's no charge on the capacitor. We connect it to this voltage source and the 3 kilo ohm resistor, and we put our switch in position 1. And a long time passes. Okay, so right now we're starting at a long time before our event at time t equals 0. So this is like, think of us right now being here at minus infinity. And so we connect it, it starts to charge up. Once it's done completely charging the capacitor though, it enters a condition of steady state. So what this means now is that we can use the principles of the behavior of the capacitor at steady state to try to figure out what exactly the capacitor voltage would be. And we can do that, we'll do that shortly on the next slide. But let's just stay where we are. We have our capacitor completely charged. What this means is that the capacitor will no longer be passing any current, but it will have some voltage VC. So again, what we're concerned with when we think of the timeline is we always have to consider whatever variable is what I'll call the continuity variable. It's the variable upon which we have a continuity constraint. And in the case of the capacitor, it is the capacitor voltage that we need to ensure does not instantaneously change. So we can calculate what the capacitor voltage looks like just before the switch changes by using the concept of steady state. The switch changes, what happens? Well, first of all, we're going to assume that the capacitor voltage does not instantaneously change and instantaneously stays at the same value. And under those conditions, the capacitor can draw some amount of current. It's not in an open circuit condition anymore. The current is more than welcome to spike from 0 up until whatever value it needs to attain to satisfy Kirchhoff's voltage and current laws in its new condition. But again, we're going to have a situation where there's a transient period after which the circuit is going to reach a new steady state. And in this new steady state, our current source here is going to be an open circuit. Our switch is going to be at position 2, and all this capacitor is going to be connected to is these resistors. And under that new steady state, we can again look at the behavior and look at Kirchhoff's laws, and then find out what happens to the capacitor voltage after a long time has passed, which I'm going to represent by the notation Vc of infinity. Okay, and that will essentially tell us what the final value of our capacitor voltage is going to be. So you can see that just by looking at and thinking about the instantaneous behavior of the capacitor versus the long-term behavior of the capacitor, even though we don't have like a mathematical formula right now for how the circuit behaves in between these endpoints, we do have certain endpoints which we need to ensure that our circuit satisfies. So that would be the VC0 minus just before the switch changes, VC0 plus immediately after the switch changes, and then the final value. So let's go see now how we can actually calculate what those time-wise endpoints would be. Let's start by considering the time just instantaneously before the switch moved from position 1 to position 2. So at this instant, we're assuming that the switch is connected to position 1. So let me highlight this position here so we can know what situation we're thinking about. But we're in steady state. We're assuming that the switch has been in position 1 for a long time before time t equals 0. And if that's the case, then because we're in steady state, the capacitor is going to look like an open circuit. dV dt equals 0, which means that the inductor current is equal to 0, which means that it behaves like an open circuit. So this current here coming through the capacitor must be 0 at this time. Now, under these conditions, what is the capacitor voltage? We can find what that voltage is now by applying the circuit analysis procedures that we're familiar with. This VC is going to be a VC for a specific time. It's going to be the VC at 0 minus. And we can apply KVL, node voltage method, any method we want right now to analyze the circuit to find VC of 0 minus. So let's go ahead and at least set up the equations for how we would do that. So first we can do a KVL around the outer loop. So we can write that 24 volts minus 3K times whatever current is passing through it. In this case, there's now a common kind of loop that we have. It's on the same branch basically with the capacitor. So the current going through the 3K resistor is just going to be 0 minus VC of 0 minus. And then we're going to drop whatever the voltage is here. So let's designate a ground terminal and let's call this node here just Vx. So minus Vx is equal to 0. But now the key is that we have to be able to figure out what Vx is. There's an easy way of doing this because there's no current coming in from this left branch. This 4.5 milliamp source, the current that it has can only come over this 4K ohm resistor. So we know that there's going to be a voltage drop over this 4K ohm resistor. Now, how does that affect the 1K ohm resistor here? I think we're going to have to define like another intermediate node here. Let's call this Vy. And we can then kind of calculate what current is going through this 1K ohm source. But take a look, because there's no current coming through this branch here, all of the 4 milliamps is going to cycle through the 4K, and it's going to kind of form its own loop in between itself here, which means that there's no kind of current left here to come through the 1K. Another way of looking at it is just to kind of follow the branch. The branch that the capacitor is on starts at X, but then through this left loop all the way over here, cycles through all these elements and then comes back to Y over here. So this is actually one entire branch. And we know that because of the capacitor, that entire branch current is shut down. It's equal to 0. Hence, there's no voltage drop over the 1K ohm resistor. And so we then can write that Vx is equal to just 4K times 4.5 milliamps. Okay, and if you solve these two equations, you can numerically find a value now for VC of 0 minus. Whatever that value is, due to the continuity constraint, however, we know that the VC at 0 minus must equal the VC at 0 plus. The capacitor voltage cannot instantaneously change. So once we have the switch change positions, we now have this connection here. Let me just kind of put it in red to emphasize it. So the 24 volt supply is essentially disconnected and removed from the circuit. We're just left alone with the 4.5 milliamp source. This VC, however, as I said before, it can't change instantaneously. So let's label this as VC of 0 plus. We actually know what that value is from our previous steady state calculation. We know what these values are. So we can use KVL and KCL to try to figure out other parameters within the circuit. For example, if we want to figure out how much the capacitor current jumped up to, remember it was 0 in the steady state case. So just to remind you, we said that IC of 0 minus is equal to 0 amps. But current can jump. There's no continuity constraint on the capacitor current. The current can jump. And what does it jump to? It'll jump to IC of 0 plus. How would we find what that value is? Again, we can just do KVL. So let's start at some point here. Or actually, we can even just start here, right? So if we come here, remember this IC of 0 plus is going to come all the way from here. So this is also I0C of 0 plus. So we can write minus 1K times IC of 0 plus minus VC of 0 plus, which is equal to VC of 0 minus. So I'm going to kind of use this relation to substitute that here. And then again, we have this situation where we need to drop over the 4 k ohm resistor. But now in this case, we don't have a non-zero current here, so we need to use KCL to find this. So if I want to find the current through the 4 k ohm resistor here, let's call this IX. How would we calculate it? Well, we have IC going inward to the node. We have 4.5 milliamps going inward to the node, and IX is outward. So we can write this as 4K times this 4.5 milliamps plus IC of 0 plus. And all of that added together is going to now be equal to 0 because we've closed our loop and we've come back to the beginning. So this is a case where all those Kirchhoff practice problems we had like on the various tests and on the study guides comes in handy when you need to kind of find these currents. It's essentially an application of the same exercise that we've just used in writing this equation. So again, if we come now to this equation, you can see we know the VC of 0 minus, and we only are left with one unknown here, which is IC of 0 plus, and we can now solve for that to find IC of 0 plus. And it's more likely than not, I didn't calculate it out, but it's more likely than not equal to 0, and you find it from above equation. Okay. Now let's take a look at what the final value of the circuit is. Again, this is the case now where our switch has been in position 2 for a long time. And when the transients have died down, we know that dVc dt is equal to 0, which means that, again, the capacitor current is going to be 0. So what does this now tell us about Vc? After a long time has passed, which I'm just going to represent with time t equals infinity. So we want to find Vc of infinity. So Vc of infinity is the final value of the circuit. How would we find it? Well, again, we just do our regular circuit analysis. Now let's look here. This was where node X was before, remember? And this is where node Y was. Take a look at this branch. There's going to be no current on this entire red branch. So again, this 4.5 milliamp current is going to kind of cycle between itself. And if we write KVL, we can write that we have minus Vc of infinity. If we just start, let's say, here we go around minus Vc of infinity, then we have to drop over the 4K supply, which is going to be minus 4K times 4.5 milliamps. And then now this is going to be equal to 0. And then from here, we can find Vc of infinity equals whatever it comes out to be. Okay, I just wanted to check on one thing real quick. Okay, so this now tells us what our final value is, and we've kind of marked all of the critical points along the timeline. The only thing that we don't know right now is how really to just connect the dots. And we get the complete picture of how we connect the dots by solving actually the differential equation. And so here's where we can really take advantage of what we know so far about Thevenin circuits to be able to represent whatever resistive circuit our capacitor or inductor is connected to by representing it with this Thevenin equivalent circuit. Okay, and now instead of doing a lot of complicated equation solving or equation writing rather, by using KVL, KCL over a more complicated network, all we have to do is use the basic principles to now write the equation using the Thevenin circuit. So let's go ahead and do that now for both cases. If we just apply KVL on the capacitive circuit, we can write that V Thevenin minus R Thevenin times IC minus Vc is equal to 0. Now, the key thing to remember when you're writing equations that have capacitors in them is that, you know, even when you're using node voltage method, is that Ohm's law does not apply to capacitors. We have to make sure we use its own fundamental relation. And so initially, we're just going to directly use the labels for the capacitor current and the capacitor voltage. And if these are not labeled for you and you're trying to write an equation, you should go ahead and make your own labels and use those labels for the current and voltage of the capacitor when writing the equations. Then we're going to substitute what we know for the fundamental relation. Namely, we know that the current is equal to C times the derivative of the voltage. And so if we substitute for the current, we can find that V Thevenin minus R Thevenin times C times dVC dt minus VC is equal to 0. And if we want to put this in standard form by just pulling out the derivative with a unit coefficient up front, so it's divide through by R Thevenin times C, collect all of the voltage terms on the left-hand side and toss any term related to the source on the right-hand side. If we do that, we'll find that dVC dTt plus 1 over R Thevenin times C times VC is equal to V Thevenin divided by R Thevenin times C. So this is our differential equation for the first order RC circuit. Similarly, we can do the same derivation for the inductor. So again, we can write V Thevenin minus R Thevenin times this time IL minus VL equals 0. But now in this case, it's the inductor voltage, which is equal to the inductance times the derivative of the current. So if we go ahead and substitute for that, we can find that V Thevenin minus R Thevenin times IL minus L DIL dt is equal to 0. And if we put it in standard form, we find that DIL dt plus, didn't want to do that. Okay, let's go back into slideshow. Sorry about that. Yes, so if we put this now into standard form, this is going to be plus R Thevenin divided by L times IL is going to be equal to V Thevenin divided by L. Okay, and if you compare these two circuits or these two equations, you can see that even though they're slightly different, they do have one common feature, namely all of the equations are in the form of a derivative plus a linear term of the variable equals to some function of the independent sources that the capacitor or the inductor is connected to. And so we're going to use this commonality to represent the differential equation in a more general form. So I'm going to write the general form of the differential equation as dx dt plus x over tau is equal to k. And so this is going to be some function. So k is going to be some function of the sources. X is either going to be a voltage or a current. And tau, if it is a capacitor, if it's a capacitive, I spelled that wrong, capacitive circuit, then we're going to say that tau, just by comparison, so if you compare our previous equation with the equation that we've just written here, you can show that tau has to be equal to R Thevenin C to maintain equality, and then for an inductive circuit, tau has to be equal to L divided by R Thevenin. And so what I mean by using separability and integrating is that what I'm going to do is I'm going to kind of reorganize the circuit so that I have all of the x terms on the left and all of the time variables on the right. And if I do that, I can write this as dx divided by x minus k tau equals minus 1 over tau dt. And so all I did was take x over tau on the other side, take a common parenthesis of minus 1 over tau, and then divide through the x minus k tau to put on the left-hand side. And then now I'm just going to integrate both sides because the variables have separated, so I can do separate integrals. So I can integrate t, for example, from t naught to some general time t. I can integrate x from some general x of t naught to x of t to be consistent with the time variable on the right-hand side. And if you go ahead and do that, the integral of 1 over x is a natural logarithm. So you'll get a ratio of natural logarithms, which when you substitute for the limits for, turns into basically something like this. You'll get ln of x of t minus k tau divided by x of t naught minus k tau equals to minus 1 over tau t minus t naught. And then if you go through and actually solve now for the general form, if you solve for x of t, you can write that x of t in general is equal to x of t naught minus k tau e to the minus 1 over tau t minus t naught plus k tau. So this is really kind of the important equation, which mathematically is going to tell us how to connect the dots in that timeline. The important thing to kind of observe here is that x of t naught here is our initial condition. Oops. This is our initial condition. And k tau over here is our final value. You can see this because if you substitute t equals t naught, which would be the event of the switch moving, then this exponential here turns into just 1. K tau adds to k tau and cancels, and you're just left with x of t naught. So when t equals t naught, our initial value is x of t naught. What happens when I let t goes to infinity? Well, t becomes much greater than t naught. You get an e to the minus infinity situation, which takes this entire first term to 0, and you're left with k tau as your final value. And so the analysis that we did in the previous slides, whereby analyzing the circuit at different points and using what we knew about the intuition of the fundamental relation to consider how the capacitor behaves instantaneously and long term, that knowledge can now be used to find the initial condition and the final value. And once you know those values, the only other thing that you need to be able to write this dynamic equation governing how the voltage or current behaves in between the endpoints is to know what the value of this tau here is. And the tau is a very special variable. It's known as the time constant. And as we'll see when we get into some plotting, it'll show us how fast the circuit either dissipates or how fast the capacitor charges. There is another way of kind of coming about to the same solution of the differential equation, which is helpful when considering second order circuits. So these would be circuits that have a capacitor and an inductor. We might consider that briefly later, but the method is universal. And that is to say to yourself, well, let's start with this differential equation. I'll write it up again to just remind you of the general form. And it's to say, well, you know what, let me just think initially about how this circuit would behave if, first of all, I consider the case where there's no kind of forcing function. So this would be the idea of in differential equations where you would first find a homogeneous solution and then a particular solution. So homogeneous solution. The homogeneous solution is the case where k equals 0. It means that you have no open sources. The particular solution is the case where you now take a particular forcing function, assign it to your value of k here, and then see how the circuit behaves under those conditions. Now, in this class, we're only going to be considering voltage sources that have constant values. And so in solving it using these time domain solution techniques. So for our purposes, K will be constant when we're finding the particular solution. And if you remember from your differential equations class, the logic we would have to find the particular solution is that whatever the form of the forcing function is, becomes the form of your particular solution. So in this case, since I'm driving my circuit with a constant voltage or current, my particular solution therefore has to be a constant. The homogeneous solution is the response when K equals to 0. And that's the one that I want to kind of consider here. So let's, to save space, let me just block out this K and set this into the 0 to find the homogeneous solution. And now let's think about when we're trying to find the homogeneous solution, and I'll use the subscript of H just to make sure that we're taking a special case here. Let me consider what type of a function I would need to be able to satisfy this equation. I need a function which, when I take its derivative and add it to itself, I can get 0. Now, the only way that I can do that is if whatever function I have, it should basically result in itself when I take the derivative, right? So let me kind of just say that again. I need a function such that when I take its derivative, it gives itself back again. Because if it gives itself back again, then I can kind of add it to itself potentially and get 0 back again. Okay, so to give you a counter example, suppose I thought that x was a sine. I take its derivative and I get a cosine. Well, then now you have the sum of a sine and a cosine. Those are never going to equal to 0 directly, right? So what function do you know that when you take its derivative, it gives itself? The only function that satisfies this logic is the exponential function. So let me assume then that my solution to the homogeneous equation is a function of the form of e to the st, where s is some constant. And now let me just substitute this general form back into the differential equation and see if there's any values of s for which I can actually solve the equation. So if you substitute this back in, you'll get the derivative, which is going to become s e to the st, plus 1 over tau e to the st equals to 0. Again, remember, we're on the homogeneous solution side here. The e to the st's are never 0. Therefore, I'm left with s plus 1 over tau equals to 0, which is when you solve it, it gives you that s equals to minus 1 over tau. What this tells me is that my homogeneous solution for the equation is basically e to the st, e to the minus t divided by tau. Now, again, from differential equations, what does this tell us about the general form? It tells us that in general, I have to add the homogeneous solution with the particular solution. So x of t in general now is going to be some linear combination of the two, right? So it can be some alpha, if you will, times e to the minus t divided by tau, plus whatever the particular solution is, which in this case is a constant. I'll just call it beta. But we have to find alpha and beta. How do we find alpha and beta? We apply initial conditions and final values. So let's go ahead and do that. Assuming that t, that we're looking at t equals to 0, right? X of 0 is going to be equal to alpha plus beta. And after a long time, x of infinity is going to be equal to just beta. So we know that beta here is our x of infinity, which is our final value. And alpha from these two equations has to be equal to what? It has to be the initial condition minus the final value. That's going to be the coefficient in front of here. Well, let's go back to what we had before. This k tau is what we called beta. This initial term up here is what we called alpha. And alpha is indeed the difference between the initial condition and the final value. And beta is indeed the final value. So both ways of solving the circuits, both ways of solving these differential equations give us the exact same result. And just to remind you again, it's this result here in the box, which basically turns the entire problem of solving these first order differential equations into a three-step process. First, you find the initial condition, then you find the final value. Finally, you find your time constant, tau, which depends on the Thevenin resistance of whatever your capacitor or inductor is connected to. And then you can substitute it back into this differential equation to basically connect the dots and figure out exactly mathematically how it's going from the endpoints that you found. So let's kind of use that to finish up the example here, right? So if I wanted to, for example, write what the differential equation was for VC, I would write that VC of t is going to be whatever we found as the initial condition. So it's VC of 0 plus, which as we know equals VC of 0 minus. So this was our initial condition. It's going to subtract the final value, which was whatever VC of infinity was. Here's my final value. Times e to the minus t. In this case, t naught is equal to 0. So it's going to be t divided by tau. What is tau? Let's just leave tau as a variable here for now. We have to define what that is. And then we add the final value, VC of infinity, which again, we found in the previous parts, just didn't work out the numbers. So we have the final value showing up twice. So the only thing left for us to do is to find the value of tau. Now we have to be careful. I'm analyzing the positive time interval. So I'm analyzing the time interval that this switch here is connected to position 2. And I have to now find what the Thevenin resistance is of the circuit that the capacitor is connected to. So what am I going to do? I'm going to take the endpoints of the capacitor as the nodes that I'm looking between. So let's label this A and B. Take this out. And now find what the equivalent resistance is of what's left. So the easiest way that we found to do that, if we just need to find the resistance, is the test volt method. But if you don't have a dependent source, the test volt method reverts to just turning off the sources and finding whatever the equivalent resistance is between A and B, which is the terminals of the capacitor. So if we go ahead and turn off this 4 milliamp source, turn it off, which means that I equals to 0. So this is kind of the test volt method way of solving it. Then you can see that along A to B, what do we have? We have a series combination of 1K and 4K. So our R Thevenin is going to be equal to 1K plus 4K, which is equal to 5K. We know the value of our capacitor. C is equal to 100 microfarad. So let's multiply the two, because we know that tau is equal to R Thevenin times C. And if you multiply it, you'll get like, what, 500 milliseconds, I think? Okay, which then you can go and substitute that into the equation here. And now this gives you the exact equation for how the voltage will behave for t greater than or equal to 0. And so now the differential equation gives us the exact mathematical format. Let's plot it. You know, we actually didn't need to have the equation to be able to kind of plot this in general. Because once you know that the functions are all going to be exponential, you can just connect the dots by using an exponential relation. Let me show you what I mean. So we have some kind of initial value for VC of 0 plus, whatever that value is. After a long time passes in position 2, it reaches a new steady state at VC of infinity. The speed at which it reaches there is determined by tau, but it's going to get there exponentially. So even without knowing mathematically what the equation was, we could kind of roughly plot this result for VC as we did here. Okay. So now let's look at the current. How would we use these same logics to find the current? Well, remember the current and the voltage are related by just a derivative. So whatever kind of dynamics we found for the voltage, those also have to be true of the current. In other words, if I find that my voltage is increasing or decreasing with a certain time constant tau, my current must also be having the same e to the minus t over tau relationship, because when you take the derivative of it, you still have e to the t minus tau. So all I really need to do to find IC is to really find the endpoints. And to do that, we have to kind of remember what we did on the circuits before to find it. So what do we need to think about? We need to think about what the value of the capacitor current is at time t equals 0 plus. And if we go ahead and we kind of go back to the reasoning, remember what we said here. Our circuit here was in position 2, but we said that the capacitor voltage couldn't change right away. So we know that this value of VC is the value of VC of 0 plus. And under those conditions, I'm looking for what IC of 0 plus is. So how would we go about doing this? Again, by doing KVL and KCL. The key thing here, I think, would be to do kind of KCL at this point. Because if you take the sum of IC of 0 plus and the 4.5 milliamps, it comes over here. In fact, this is seeming a little bit familiar. I'm wondering, I think we did do this before. Let me just kind of go double check so I'm not repeating myself. Yes, we actually wrote the equation that we needed to find IC of 0 plus right here. So we know what IC of 0 plus is from that calculation. I'm not going to repeat it. But now we have to find what the value of IC of 0 plus is in its final value. Again, this is where our switch is going to be. And remember, in the steady state, the capacitor looks like an open circuit. So actually, we know that IC of infinity, therefore, has to be equals to 0 amp, because the capacitor behaves like an open circuit. Okay, so how do we relate these together? Let's write IC of t. Now remember, when it was in steady state just before the switch moved, the capacitor was an open circuit, so the current was 0. And after it moves to switch 2 and it's been there for a while, it's again an open circuit. So it's again back to 0, but instantaneously it will jump up to whatever the value was at IC of 0 plus. So it'll jump up, but then it will again exponentially drop and die down. So it'll have some exponential relationship, which now connects the 2 points. So, you know, we could even draw it without writing out the math exactly. If we want to actually write what this equation was, though, we could still use the same results from the differential equation. We would just be substituting different values of initial conditions and final value. So IC of t is going to start with an initial condition of 0. No, I'm sorry, it's going to start with an initial condition of IC of 0 plus, right? And then its final value is going to be 0. This is going to be e to the minus t divided by tau, where tau is the same R Thevenin times C that we found and used for VC, and then plus the final value, which is 0 here. So we can use the same logic now to write the mathematical expression for the function that we've just plotted as the result for IC. Okay, this concludes kind of the initial example that I wanted to go through from this initial lecture. I am going to be posting some study problems for you to kind of go over and look at the calculations for. If you have any questions, please send them to me by email. I'll do the best I can to hopefully post some videos in response, or at least post some written explanations and disseminate that to the entire class so that everyone can benefit from whatever questions you have. So again, please don't be bashful. I know it's difficult trying to do things when you're in an online format. The best way that we can overcome that is by y'all trying to get in touch with me and communicate your questions to me as often as possible so that I can try to address them as best as I can. Take care, and again, let me know if you have any questions.